Final session of the day. There's one very important information that has been left out. After Javaforum, we are a few guys and girls who go to Bishop Arms and drink beer. Nothing official, but we like to meet up, drink beer, and talk about stuff. Feel free to join. The other thing to note about this session is that this is about Kotlin, and I know that this is Javaforum. I will not explain every piece of the syntax that I do, and I think that is quite comprehensible for a Java developer to read Kotlin. But if it's something that is kind of what the hell is going on there, feel free to interrupt me, and I'll do my best to explain. So a few words about me. My name is Ola Petersson. I'm a full-stack developer, has been working in the Java ecosystem for a few years. I work with most of the stack and also like development processes, etc. So I also occasionally do conference speeches and Javaforum speeches, which has taken me across Europe and to the US, where I became a JavaOne Rockstar a few years ago. And there's two reasons why I'm telling you this. One, whenever I bring this up at home, my girlfriend just hushes me. She says, this is not interesting. So now I take the opportunity. But two, I started on this stage. So if you are curious about doing conference talks or sessions, or you want to share knowledge that you gain, reach out to Thomas or Squid, because they are often looking for speakers and are very keen on making this for the community. If you want to reach me, the easiest way is to do an ugly hack at Twitter to go to Ola, and you will find me there. I work at a company called Meltwater. We are having a few different offices around the world. The one in Gothenburg is quite cool. We are by Avenyn. We have one of the largest Elasticsearch clusters of 2.5 petabytes. We also have a Kubernetes cluster of 100 plus pods. And we build our applications around these two services. So if Meltwater sounds interesting to you, grab me after this speech and we can talk a bit about what we do. Okay, let me take you back in time to June 2018 when I joined Meltwater. And I joined Meltwater on a top secret mission. And the mission wasn't really top secret, but if you look at this animation, you kind of have to write top secret. It's so cool. Okay, so it wasn't top secret. What I was gonna do with my team was that we were gonna consume every message from the social media platform Totvovi.ror, from here on referred to as Twitter. And we were going to consume this in a microservice architecture. Now, the thing about Twitter is that every second, on average, around 6,000 tweets are tweeted. So this means that we need to be fast. Now, when I joined, a few pieces of the puzzle were already in place. It had been decided that we were going to go for a microservice architecture. And if you look at microservice architectures, what you usually see is that you have a few different services that need to communicate between each other. You might also have persistence or databases that the service needs to communicate with. And this quite often happens over HTTP, doing I/O operations. So you have communication here and communication here. And the thing when you have a lot of I/O operations is that you can't really buy a faster CPU. That won't really help you because you're not computing anything with the CPU. But rather what you try to do when you want to go faster is maybe to think about parallelism. How can we do two concurrent calls? How can we, instead of waiting for every call to finish, do what is not related to each other in parallel and speed it up in that way? And I found this very interesting. And if you have seen me here on Javaforum before, you know that I have talked about completable futures and Akka and all of that stuff. But there was a second decision that was already in place when I joined Meltwater. And that was that we were going to go with Kotlin. And when you start to look at Kotlin and what they offer in terms of asynchronous mechanisms or dealing with stuff in a non-blocking way, you soon start to find coroutines. So this is what we found out, that there is this new thing. It was experimental at the time, but soon to be stable. And we started to Google for it and look at the tutorials, and we soon found the first example. The first example that you will quite often see is that if we take a number or d numbers between 1 and 1 million, and we then take these and map them to our first coroutines. Now, to create a coroutine, you need to have a scope. We will use the global scope, which is there by default. It's provided by Kotlin. It has a global scope. It's accessible everywhere. Now, we can use this to call something that is called launch. A launch is basically a fire and forget, but it takes a side step, like when you come in your main thread and you start off another thread. So this means that when we do the launch, we fire off this and tell it, go do something there, and let me continue with my loop. So for now, I will just let this coroutine sleep, or these 1 million coroutines sleep for a second. And then we will print line that it's finished. This was the very first example that we saw on the interwebs. And as you see, after a while, it prints finish, and that's it. Not very exciting. Not very exciting at all. So why is this the first example that you will stumble upon when you try to understand coroutines? Well, let's have a look at what would happen with a similar implementation in Java. So again, we take the numbers between 1 and 1 million. We then create a new thread for each of those numbers, and we just let that sleep. And after that, we print that it finished. Now let's do a questionnaire. Who here thinks that this will finish in about, it says 1 second, but as you see, in about 5 seconds? No one believes. Who believes that this will never finish? It should be the rest of you, because nobody believed in the first. So let's try to run this. Oh, it finished in about 1 second. Unfortunately, with an out-of-memory error. And this is the reason why this is usually one of the first examples that you will stumble across. Because the coroutine creators are really trying to push that coroutines are like lightweight threads. So the reason, of course, that we got an out-of-memory exception here is that each thread takes about 1 megabyte of memory or 2 or whatever it is, and eventually we run out of it. Whilst coroutines are obviously more lightweight. So this is what we took to heart. We said, okay, we can translate that in our brains. We know how to work with threads. We are Java developers. So let's just work with these lightweight threads instead. So we had some old code where we were doing database calls. I have here a Dynamo fake client. And we started to do parallel execution of our database saves to speed up the process. Now, we didn't really have 1 million parallel executions, but maybe 32. And what you should know about the Dynamo fake client is that this emulates a network call, so it sleeps for 1 second. So we did this. Amazingly easy. We have lightweight threads. Pretty cool. Oh, I will actually realize that I lied a bit to you before. Before everything finished, because nothing was computed, we also need to wait for all of the coroutines to finish. But it would still work. You will have to believe me on that. So what I just did was that now we fire off 32 parallel database calls. We are then waiting for all of them to finish. And then we are right now print lining finish. And we put this into production, but soon saw something which didn't really fit our then belief of this. So we did what every developer does. We started to measure how long time this execution did with system current time millis, of course. And we then ran it. This is a bit weird. It took 4 seconds. But we did our lightweight threads in parallel of 32, which should only have taken 1 second. So back to the internet and back to trying to understand what coroutines are and how they really act. And we soon found out that coroutines differ from threads in a very substantial way. We found out that coroutines are indeed lightweight. You could run 1 million of them in parallel, but they are not threads. So I'm going to try to explain this. I'm not very smart. I'm not really a computer scientist, so I will explain it with something that I can relate to, which is eating pizza. So when you have a thread which gets some kind of data to act on, maybe a for loop or something, you start to use the CPU to chug away your pizza slice. And the thread is doing work and sitting there and eating. But after a while, you're out of pizza. And what do you do when you're out of pizza? You call for more pizza. So you do a new network call to the pizza service, and then you sit there and wait for a new pizza slice to get delivered. And if this is a blocking operation, if you're not doing anything else, you are taking this full resource, which is my kitchen, and just blocking it. You're just sitting there. You're kind of useless. Now, coroutines are a bit more hipster. So they are still running on threads in the beginning. They are still existing in my kitchen. And they are still able to perform the for loop of eating pizza slices. But after a while, the pizza is out, and you make a phone call for more pizza. This is where coroutines differs from threads. Because when the coroutine says, okay, I'm going to block for a while, let me get out of here. Let me free up the space, the thread, to let somebody else come in, take the chair, and eat their pizza slice. I'm going to try to explain this in code as well. And if you found this uncomfortable, I promise there will be no more videos of me eating pizza. In Kotlin, there is, or when you write coroutines, you will have to start with the suspend function. I will talk about the suspend keyword. And we write get pizza slices function. Now we let this return a sequence of pizza slices. It's actually only called slice. And let's print line that we are starting to bake slice 1. We can then here yield a slice. And then let's say that we are starting to bake slice 2 and yield a slice 2. Now, sequence in Kotlin, you can think of it as a list. The only difference is that a sequence can continuously produce elements, so it's not necessarily finite. Now let's call our sequence of pizza slices. And for each of them, say that we are eating just the index of our pizza slice. Now, if we run this, let me bring out this a bit. It kind of looks normal at first sight. But if we think a bit about this print line here, or the standard out, it's quite confusing, at least it was to me as a Java developer. So what you're seeing is that we are starting to eat pizza slice 1 at this line, or starting to bake slice 1. We are then eating it. Then somehow we are jumping into the middle of a function to start to bake slice 2. And this was, as I said, to me as a Java developer, this was a bit confusing. Like, how can I enter a function in the middle of the function? How does this to return type work? And what the Kotlin compiler is doing when you start to look at it is that it uses a pattern and an interface which is called continuation. The continuation is quite easy. It has a coroutine context, and it then has resume and resume with exception. And what happens is that when we write the keyword suspend fun get pizza slice, what the Kotlin compiler will do when it generates the Java code of this is to produce this signature, where you return an object and then also attaches a continuation object or implementation of this interface for you. And they then use this to build kind of a state machine. So when we yield, we do return the slice, but we also return this continuation. This is nothing you see. You see the same code as I wrote, but this is what the Kotlin compiler does. And this continuation has a reference to the rest of the code. So the middle of the function where we jumped in. And after a while, eventually we terminate this whole sequence. And this is the same, or the continuation is the thing that Coroutines uses to say, okay, I'm gonna block for a while, so let me just go to sleep. Let me go out of the way. And when you wake me up, when I have the result, I will continue with my continuation. And this allows us to leave the kitchen, free up the thread to let others work on that thread. And in that way, we can write non-blocking code. So that is what coroutines are and a bit of the benefit about them. But it's more. So it's more about how they function. But why should we go for coroutines when we have our threads? Well, let's think a bit about how we are writing our asynchronous code in Java. Now, if we have a pizza service here, this pizza service has a few functions with completable futures, the same futures as we use in Java. And how this code usually works is that we get the pizza async, we get the completable future, which we can then apply our next operation on. And when we have the pizza service, we can start to slice the pizza. And after a while, we get the result of that, etc., etc., etc. And what you see with this code is that, well, you better lower your font size, because I'm soon running out of space. I'm running to the right here with this callback style code. And that is, I mean, it's fine. I do like completable future, and I think they are good. But they are quite different in the style of it to how you write your synchronous code. Nobody would look at this and say, yeah, that makes sense. It looks exactly like synchronous code. But with coroutines, you can do this easily. So if the get pizza is a suspending function, if it has this option to go to sleep, you can write your non-blocking code like this. And this looks extremely much like synchronous code. Now, this do look like synchronous code, but if you look at the IDE a bit closer, out to the left, you'll see that there is a small icon here with an arrow and a green line through it. This means that Kotlin has identified that here is a suspending function. This is a point where I could leave the thread, sleep for a while, and then get woken up. So this is non-blocking code. Of course, this doesn't necessarily give us a lot of performance gain right now, because we are only doing non-blocking, meaning that we are not using the resource when we don't have to. But we said that we also might want to do things in parallel. And in Kotlin and Coroutines, parallelism is an opt-in. You have to really be sure that I want to do something parallel. And that is something we saw in the first example that we had when I did the launch. This is a thing that starts parallelism, starts a different track. There is also an async function. And the difference between those two is that the launch is the fire and forget, whilst the async is when you're actually interested in the result. So the return type of this right now is, I don't know if you can see it, but it says deferred unit, and unit is kind of the void type since we are not returning anything. Deferred is the same as the future wrapper in Java, or completable future. So if we actually want to have the value we call await. And as you see out here to the left, the await is also a suspension function, meaning that when we evaluate this, we could free up resources. Okay, so I think this is one of the biggest benefits with Kotlin. The code that you write synchronously versus the code that you write asynchronously look kind of the same. And for your Java purists out there, there is a very interesting project going on with fibers in Java, which is similar to this. Okay, but one of the main selling points with Kotlin is that it's interoperable with Java. So do they even speak future? And they do to some extent. Now, what you can do in Kotlin, if you haven't looked a lot at it, is that you can do extension functions. So I can, on string, add a new function that is called pizza. I can then say, on any string, exercise, call the function pizza. And if I run this, we will actually print pizza and not exercise. And what the coroutine maintainers did was that they wrote extension functions like this on the completable future. It might be on the completion stage, but the main point is that if we have a pizza service in our old code, which has these completable future signatures, we can do await. And this is the extension function on completable future. You can now see that we are now allowing to free up this resource, and it injects in the completable future lifecycle to make it speak coroutine lifecycle. So it's quite cool. You can still use your old completable future APIs, and you can make it look like coroutines and work like coroutines. When we did this, we had some old Java SDKs towards Dynamo, I believe, which only used futures, like the old Java 1.6 futures. And if you are stuck with futures, you cannot do these kind of extensions because they don't have that kind of life cycle where you can check if they are done or not. They just have the get, which is blocking. What we decided was that whenever we are stuck with old future APIs, let's just stick to the thread model. Let's not mix and match between threads and coroutines, because it just became too much to keep track of. Okay. So then what about shared mutable state? Because if we start to do things in parallel, and if we have a lot of coroutines happening in parallel, they might need to update some shared mutable state. And what we started off with in our classes was that we used the synchronize keyword. The synchronize keyword that we all know. It still works. Coroutines are still running on the threads. But there is a better way to do this. So if we have a counter in Kotlin, we can create something which is called a mutex object. If we then have a function to add to this counter, we can say, hey mutex, this mutex object, act as a lock and do the counter ++ operation. And this is essentially the same as using synchronize. This will put a lock around your counter. The main difference between this and using synchronized is, as you see in this left pane again, that we can suspend and free up a thread when we are locking. You cannot do that if you are using synchronized. But it's still possible to use synchronized to protect your state. There is another very cool feature that the coroutine people are working on. And I will do something that you should never do when you present on stage, but I will show you a lot of code in one go. What the coroutine guys are now trying to include in coroutines as like a first order citizen is actors. And what you're doing is that you are encapsulating your state within an actor, within a coroutine. And the only way to then communicate with this actor is by sending it messages. And this coroutine actor will then assure that only one message is processed at a time and protecting your state. So this is quite cool. This is an experimental feature, as I said. I haven't worked a lot with it, but if there are any Go fantasts in here, I know that they are also working on channels and selectors. So there's a lot of things happening in the coroutine space. Okay, that's the shared mutable state. Before I leave, I have a very small example still here today. And I just feel like I have to say it. We are a backend team, and the life cycle of our applications is usually the same as the JVM process. But I know that a lot of people are writing Kotlin for Android, for example. And what I've been doing, my computer might have frozen. Okay, let's take this here instead. So you have seen that I have done the global scope launch here today. And it's a bit dangerous to do global scope launch because if you have a bug in here, or if you have something that is like a while true, for example, you might start to leak coroutines. And it's still, they are lightweight, but after a while you will run out of memory exceptions. So you could use something that is called coroutine scope and have your launches and asyncs in here. What this does is that it scopes whatever is going on here, making sure that this does not return before all of the fired children coroutines have finished. I will not delve deeper into this. It's a very interesting subject. They are calling it structured concurrency and coroutine scope, and you can read more about it on the coroutine official documentation. That is also where I would recommend you to continue from here if you are interested in coroutines. So read up on structured concurrency and the coroutine scope. It's quite interesting if you want to build robust applications. If you are interested in thread pools and wondering well, how can I determine what should run where? That's called dispatchers in Coroutines, which is also an interesting read. And then I could also recommend Ktor, which is a Kotlin framework built on Coroutines, if you would like to start to elaborate with this non-blocking functionality. Okay, if you want to get these slides, I will publish them on slides.olapetersson.se. And that's what I had to say here today. Thank you.